Проверьте, да, что мы...
Ой, кстати, да, надо проверить, потому что не было запланированной трансляции.
Опять не было? Сейчас,
нет, я же не вижу.
Great. So now I want to speak about density and density theorem. So yeah, so okay, so let us discuss density theorems. So the question is the following. Suppose you have the group, so algebraic group, and algebraic subgroup. So I find, and you ask yourself the following question. So take your group and take all its conjugates. So this is a subset of the group G. So what can be said about this subset? Yeah, so what can be said about this subset? Yeah, so what we are going to do now is to give some conditions that, first of all, so this is precisely what is called density theorem. Closeness. And so the following just G of H algebraic groups. So then the first is closedness, that if G mod H is complete, notice that so this set is infinite union of closed subvarieties. Yes, so H is a closed subvariety. So this set is infinite union of closed subvarieties, but nobody guarantees that it will be closed. Yes, so only finite number of usually finite number of closed subset gives you closed subset for infinite. It is not clear. So the closeness precisely is the closeness criterion. So if G mod H is complete, then this subset is closed. This closed subset of G. Да не, ну давайте тут лучше так. Окей, and the second, ну ладно, давайте его обозначим. Хорошо, уговорили. And the second tells you when this set, so notice that this set is, a priori it can be even not algebraic, because it can be too big, because you take, I mean, it will be constructible because it is, sorry, it will be algebraic, but you cannot say it is just closed or open. And the second is the conditions when it is dense. Yes, so suppose that H has a finite number of fixed points, on G mod H, then Y is dense in G. Ну да. Ну, как? Ну, вот, как бы, как всегда, но на однородном пространстве G может действовать с одной стороны, поэтому единственное нетривиальное действие H на G по H это следующее. H переводит смежный класс GH в G H, G, H, да? Все, больше действий нету. Ну, как бы, ну, можно как бы говорить, что это сопряжение, тем не менее, смысла в этом все равно, нету, да? Ну, можно говорить, что это пришло из действий сопряжениями, да? Но в этом немного смысла, как бы, в таком виде. So, Y is dense, the risky dense in X, in G.
So G mod H was a homogeneous space in the first paragraph, and now H has finite number of fixed points.
Yes. On this homogeneous space. Yeah? It's same space. Не, просто... Нет. So these statements are unrelated. They just put in one theorem because they are usually used together, but and because they're proved similarly, so that's why we're putting it together. Okay. But here I wish to, the first claim follows from a little bit more general statement. So just first follows from more general statement. Yeah, so actually notice the following remark, so that, of course, there is a map, yeah, so that you can obtain Y, Y can be obtained via the following map. We are taking G times H, so you can look at it as the subset of G times G, and you can map G times G as follows. So you take G here, you take G tilde here, and G tilde here, and you map it to G G tilde, G tilde G inverse, yeah? And then you can take the corresponding projection on the second factor. Yeah? So this, the image, so so this set, what we're interested in, is obtained as the image of this composition. Yeah? So this phi and pi 2. Yeah? So just y is equal to applying phi and then pi 2 to g times h. Yeah, so you just take all elements of the pairs g and h, and you take all images where h runs through the elements of h. Yeah? And it is just the part of the diagram that will be needed for us later. So what what is more general statement, notice that you take h as a subset of g and you start acting on this h. So the more general statement is the following. So suppose y is a subset in x. So x is the variety with g action. Is the algebraic variety with g action. H is a subgroup, algebraic subgroup. Yeah, so G is affine, algebraic. And Y here in X is a closed H invariant subset. Yeah, so meaning that HY sits inside Y for any H inside H. Yeah? So then assume also that G mod H is complete. Then I claim that if I apply G to Y, so meaning that this is all possible set of points, action of GY inside X, where G belongs to G and Y belongs to Y. Yeah, so I claim that this variety is closed. Of X. Okay. So this means the following. So you have the following situation. You have G and say acts on X. Yeah, so G acts on X. And you have the invariant subvariety Y. So you all points. So you have the subgroup H, and it maps the points of Y in the points of Y. So then I start taking Y, and I'm applying elements of G. So of course, Y will be moved along your, so somewhere in X. So the claim that this subvariety is closed. Yeah? So what you obtain. Okay? So it is closed algebraic subvariety of X. Yeah?
In our case, Y is that Y or not?
Чего? In our case, no. In our case, X is just G. So H is equal to Y. So that Y Yeah, so that's why let us call it Z. I mean, since we're in Russia, this, at least this letter is not bent. And you wouldn't be confused. So let us be modest and say that it is due to my name. So yeah. So let us put so Z will be H, and the action is just G. So G acts on the point of Z just by conjugation. Yes. So okay.
So is it true that we are proving the more general theorem to prove the first part?
Yes, it will be completely the direct corollary. So this will be direct corollary of that theorem.
So if there is a complete G-bias and there is a closed invariant subset, then this the orbit of Z is closed as well.
No, I mean you are not speaking about orbit, but the G span. Yes, so the union of all orbits of the points from Z. Yes. So. Yeah, so you have, of course, it can happen that the orbit return to the different point of Y, but you are taking, so the orbits do not intersect, of course, but you are taking the whole union of this set. So let us prove it. So the idea is to prove completeness, and actually to realize this as a closed subset. So this is closed algebraic subset. Yeah, so notice that Z is sitting inside X. So you can do the following. So you can take G times Z. Yeah, so you want to consider all, in the end of the day, of course, you want to map it to X and consider all possible, so the suboriented GZ inside X. Yeah? So this is obtained as follows. So first of all, you can do the following. So take the map from GZ to Z. Yeah, so you have, yeah, so this is, of course, the subset of G times X. Yeah? And here on G times X, you have the map again to G times X. And the map is as follows. So this map is just map X, G and X to the point, to the collection of points G, Gx. Yeah? So you are just taking the G span of possible elements that can be obtained as the image of G. And then you just can do the following. So you can project this to G mod H times X. Yeah, because you have natural map. So there is natural map pi from G to G mod H. So you can project it. Yeah, so you can use pi times identity here. And then the idea is that you can now project it to the second factor. And notice that if you take the restrictions of this composition, is just to G times, so the restriction of the composition to G times Z is precisely G times Z.
Last map is projection by second factor, yes?
Last map is, yes, projection.
It seems like it's no sense because we did something with the first component of product and then just took second. So we can...
Не, ну вы подождите, ну как бы мы тут, так сказать, систему залпового огня спрятали, а вы, так сказать, это... Yeah, so the idea is that we take G times Z, yeah? And look what happens if you apply this composition of psi and pi times identity and P2. Yeah, so if you apply psi pi times identity and P2, then this is just as a set, it is just GZ. Yeah? You are applying here, you are taking the points GZ, you are mapping to G times Z, then here you are applying mapping to this quotient and this, yeah, so maps to the point x, yeah, so gx, and of course when you where x belongs to z, and then when you project to x, you just take gz. But the claim is the following. So claim that first of all, if you look at what is the composition of GZ here? Yeah, so the image of psi and P times identity on G times Z is a closed subset, so it is a subset in G mod H times X. So I claim that it is a closed subset. Then you see the following, that this is a closed subset, and then I obtain, let us put it to be W. So and then you are taking the projection of to X, and the image of W is precisely G. So G mod H is complete. Yeah? So since G mod H is complete, then this means that P2 is closed. Yeah?
How is it typically, how does typically completeness proved? It is quite a strong condition.
Yes, and actually I didn't tell it. Yeah, so let me notice the following. That for homogeneous, so you have, after we proved the Borel fixed point theorem, then corollary of Borel fixed point theorem So this is the following. So G mod H is complete if and only if H contains some Borel subgroup.
So for algebraic groups, the completeness property, implies a strong condition on the structure of this group.
Yes, and actually the idea is that usually the conditions on algebraic conditions on the homogeneous space should imply some structural. So the usual game is to impose some algebraic conditions on homogeneous space. I mean algebra geometric conditions, and try to understand what properties. So what conditions do you have of on H as a subgroup of G? Yeah, so as defined in some set, in some other terms. So here, for example, the completeness, which is not related with just a priori not related with some subgroups, gives you that very precise property that. So of course, so H, in a sense, when you're speaking about homogeneous space, H is defined up to the conjugacy because you can pick up different point and different, so it will have different stabilizers, so which will be conjugate to H. So that's why this is more or less considering homogeneous spaces, considering H up to the conjugacy. So this condition says that up to the conjugacy, H contains the Borel subgroup. So, and we can derive it, so the proof. So notice that already if this holds, so if H contains B, then it is very easy. Yeah, so because you can pick up G mod B and just map it to G mod H, and this will be algebraic map. So if this is complete, so this we already know that this is complete, then this implies that this is complete. Okay?
Okay.
And vice versa. So suppose, again, we already proved it, but we didn't notice. So if G mod H is complete, then B is the Borel, yes, so that B has fixed points, on G mod H, and this means that the fact that BGH sits in GH implies that B, G inverse B, yeah, so that H sits in B inverse, in G inverse GB, as we have already proved. Yeah, so sorry for not formulating this statement in this way, but we have used it all the time. And this, of course, implies this corollary and tells you that more or less this is very acceptable criterion, but however, yeah. Yeah, because it is misprint here, yeah. Because the inclusion is that BGH is here, so H is bigger, yeah. I mean H maps here, and So this means and the G maps here, yeah. So that
So we can erase H on the right.
so this yeah, well, this means that for any element of B, BGH sits inside the GH. So in particular, you can erase this one, and this gives you inclusion that B sits in GH G inverse. Yeah. So this means that Borel subgroup sits inside the GH G inverse. So this means that H contains some Borel subgroup. So yeah. So and what we have to notice here that so the non-trivial moment is that W is closed, but notice that so phi is isomorphism. And this means that psi of G times Z, so it is isomorphism on this set. Yes, so it is clear. You can write down the inverse. So this is closed. And the only thing that is remaining that to see that W, so W has the following properties of when you are mapping W to G times H times X. Yeah. So notice that W contains all the preimages. Yeah. So that what points can lie in the preimage. Yeah. So and if you look at contains all fibers, and all these fibers are of the same dimension. Yeah, so this fibers are of the same dimension. So fibers of P times identity. Yeah?
So we consider V as...
So not psi of E. Yeah.
Okay.
Yeah. Sorry. Yeah. So you are taking. So you are mapping it here. Yeah. And then you take it here, and you consider the image of pi times identity. So I claim that so the image, so this is definitely a closed subset here, but I also claim that this is closed subset here.
It's exactly definition of completeness.
Нет, это мы уже вот здесь воспользовались. Нет, вы уже пропустили, так сказать. У нас уже... Нет, в смысле, что, ну, как бы образ W здесь, ну, в смысле, вот под... я W вообще-то уже... Да, я... Сейчас... Да, W уже вот здесь, да, то есть, ну, как бы... W то есть, поэтому... не W содержит, то есть, ну, надо написать psi от G на Z, да, вот, которое отображается в W сюда, ну, как бы, оно как раз, оно содержит, ну,
W у нас в GPH.
W не в GPH, а, ну, в произведении.
Ну да, в произведении же.
Да, я уже обозначил в произведении. Да?
Значит, мы должны взять
Ну, мы должны...
еще композицию с P от...
Не, ну да, но вот эта вот композиция
Ну, да.
P на identity, да, ну, как бы вот оно W. И ну, вот замкнутое является вот это множество, и оно, so it contains all fibers of the same dimension. Yeah? And if there is lemma that I want to postpone, so lemma that so suppose you have x and y, and all fibers, so all components of fibers have the same dimension. So all components of fibers has the same dimension. And suppose you have W inside X, so some subset such that W W is equal to taking the image of W and then taking pre-image, so meaning that it contains all the fibers, yeah, so that intersect it, so contains all the fibers that intersect it. Draw. Yeah, so just suppose you have the morphism from x into y. And it has the property that you take the fibers and all components of the fibers have the same dimension. Then suppose you take all irreducible components. So irreducible. Yeah. So if yeah, because it can happen a priori that yeah, so this will be a connected component, but not irreducible. So if you have W, the subset which is entirely contains all fibers that intersect, so that means you take image of W and then pre-image of W. Then I claim that image of W is closed, f of W is closed in y.
So if the double is the set of all fibers, then the image of this set of all fibers is a closed subset.
Yeah, yeah. I mean, a priori, this map is not surjective. Yeah, so it can be not surjective.
So can I imagine it as some kind of bundle map?
Yeah. So yeah. So you should yeah. So imagine it more or less like so this picture. So you have so the subset. So here it maps to y, yeah, and here you take W, which contains entirely all the fibers, and the claim is that f of W is so f of W is closed, yeah. So this is closed, and so it has the property that you have taking the image and pre-image, and all fibers are contained here. Yeah, so a priori W can be smaller like this, but still it has the image. But it contains all the fibers that it intersects. So it is image and pre-image at the same time. And then, so the claim is that here it cannot happen that this map is not, so this is not closed. And notice that this is not, I mean, if you think of this as the map from hyper A2 to A1, just this is not a counterexample, yeah, because I mean the image of this closed set is not closed here. However, I mean, if you look at the fibers, it doesn't entirely contain it. Yeah?
So what's wrong? Here's a fibration, yeah?
So here again, the map for, so X is A2, yeah? And the map is to A1, so the first condition of equidimensionality. So this is called equidimensionality of the morphism, the first condition. It holds, yeah, because the fibers are of the same dimension. But they are badly related with the image of with W, because W just intersect them and do not contain entirely.
I don't understand what is wrong with... why does this example don't comply with the lemma?
Ну, в смысле, потому что, ну вот, если вы вот это получите W, то W пересекает слои, но не содержит их целиком. А в лемме говорится, что W содержит целиком все те слои, которые пересекают.
Ну, если взять W, то есть гипербола это W, да?
Да, гипербола это W.
Если я возьму f от f минус 1 W, то получу всю плоскость.
Ну, правильно.
И это уже будет удовлетворять.
Ну, а это удовлетворяет, да, потому что она в А1 отправляется. Нет, это же не контрпример к лемме, это, ну, контрпример к тому, что если условия леммы нарушаются, то...
Do we assume that y is closed in X?
You mean what y is closed?
Should y be closed in X or not?
It's just a
It's image. Y
No, y itself.
is closed where?
And in X.
Ну, в смысле, у вас же отображение из x в y. Вы имеете в виду f от x?
В утверждении леммы
Да.
у нас W это любое подмножество или оно должно быть замкнуто?
W замкнутое, да.
Наверное, надо написать.
Да, я... Ясно.
Yeah, and we have the phi of...
Yeah, and here we have to check. Yeah, so in order to apply this lemma, here we have, of course, to check that so the claim is, so if you want to apply the lemma, so the claim is that you want to.
Если мы просто предполагаем, что на X задействует транзитивно, да? Понять, что это изоморфизм или нет.
Где? Вот здесь?
Вот вы написали, что пси это изоморфизм.
Ну, потому что вы обратный можете написать. На парах-то оно же не на x изоморфизм. Ну, в смысле, если же x перевести в пару g в минус 1, по этому элементу вы восстановите его, да?
Окей, да.
Ну, как бы, so the psi is inverse to each other, yeah? So, yeah, so you have just the inverse of psi is just mapping gy to, I will just write, yeah, so just g inverse of y. Yeah, so, so here you have to notice that just if you put, yeah, so the claim is the following. So if you have, so what is our subset? So the subset is obtained by the set of points gz. So so the claim is that if you change so this is just a point of W. Yeah? So this is a point of W. If you want to prove that if you have the, so you want to find the inverse. So I claim that this is precisely the inverse of this map. And the reason of this, that of course G, of course G lies in the preimage. Yeah, so it lies in the preimage pi times identity of W. Yeah, and if you change G by any H, yeah, so of course you can change so Z and the G. Yeah, so you can write it down GH here, and but for the price that you are changing Z. Yeah, so you are changing Z by H inverse, and notice that H inverse of times Z, it belongs to Z because Z was invariant, and so this implies that this also belongs to pi times identity inverse of W. Okay?
So the fiber is isomorphic to H?
Yeah, so fiber is just isomorphic to the coset. Yeah. I mean, it is clear that the fiber is isomorphic just for, it's clear here that the fiber is isomorphic to the coset, but it wasn't clear that that W contains the whole coset, and in order to guarantee this, you should write it as follows. So that just, I would say that this should be written as so you can denote this as G tilde and this as Z tilde. And in order to say that this belongs to the psi of something, you should write it down as G tilde, Z tilde. Yeah? So this belongs to psi of G times Z. So in order to say that this belongs to the preimage, yeah, so this of course belongs to the preimage, but to prove that this belongs to the image, yeah, so to prove that it belongs to psi of G Z. So you have to write it down. We have to write it in this form. Yeah. Okay.
То есть мы здесь как раз пользуемся тем, что оно инвариантно, да?
Что?
То есть мы здесь пользуемся, что оно
Да, да, ну как бы иначе, ну то есть что оно содержит все слои, а значит должно быть замкнуто. Okay. And there is this is a part of a more general statement. So this yeah. So this so about this lemma I want to talk later because it will be a little bit. It's not very complicated, but it will be long. So I will tell. I will be speaking about it next time. And so this part is clear. Yes. So we have the second part of the theorem. So just I want to raise something. Okay. Так все понятно, да? Стираю, да, тогда вот это. And also we have the density statement. So the density statement was as follows. So H has a finite number of fixed points in G mod H. Then just so this set is dense in Y. And of course, in G. So of course, I want to. So I will be writing the same picture, but with the x equal to G here. Yes. So Z will be now equal to H, and the x is now equal to G. And but also I shall take. So in order to. So at the last step, I also will take the second projection, but it will be convenient to take two projections here. So 2px and 2p G mod H. Yeah. So what is the claim? So notice that, of course, the projection. I want to do the following. So in order to prove that it is dense, it is sufficient. Yeah, so now I want to apply everything to G. So this means that let me erase it. So I shall put x to be now the just element of G, and the action will be by conjugation now. Yeah. Okay. And here I shall put. So this is Z equal to H. Yeah? So here the action will be by conjugation, and. But everything will be the same. Yeah? So X is just the whole group G. I just wanted to write different letters to emphasize, so to have less letters G here. So because here there is the picture is not symmetric with respect to changing G's, so that's let me keep this notation. Okay. So the claim is, in order to prove that this set is dense, it is sufficient to prove, so sufficient to calculate dimension of Px of the set W. Yeah. So. The W is just defined as taking G times H and applying psi, and then applying pi times identity. Yeah? But what can be said about W? Yeah? So first of all, notice that dimension of W. Yeah, so just you start. So you know what is the dimension. So you have G and H. Yeah. So dimension of W is equal to dimension of G times H. Yeah. Sorry. So. I want to say that if you apply psi to G times H, it is isomorphism, so the dimensions are equal. Yeah? And then if you think, so if you look at pi times identity, then you see that it contains fibers, and all fibers have the same dimension. Yeah? So that fibers just psi of g times h contain fibers of pi times identity, and their dimensions of dimension equal to dimension of the coset. So the fibers were identified with the coset. So which is dimension of H. Yeah? So it is dimension of H. So you see that dimension of image of the dimension of W here. So the dimension of W is just what is dimension of G plus dimension of H. It is dimension of the product minus the dimension, so which is dimension of psi of GH, minus the dimension of the fiber. Yeah? So dimension of the fiber, which is H. Yeah? Okay. So the dimension of W is just a dimension of G. Yeah? Okay. And so the claim is that now we have to check that. Yeah, so at least now you see that the W is a proper dimension. So W is some set of dimensions smaller than yeah, so W is some subset is of dimension of G, and it maps to G. Yeah, so I want to make the following remark about so suppose you have the morphism from X into Y, and suppose that dimension of X is equal to dimension of Y. Yeah, so you know that. So just how you should check that. And you know the equality, so by Chevalier theorem, semi-continuity, yeah? That dimension of the fiber is bigger or equal than dimension of X minus dimension of image of X. So if you find the point, so if we find a point such that, so a point Y, so such that dimension of the inverse of the preimage is 0, then it will imply that the general fiber, so the fiber is finite. Yes, so this here, the fiber is finite set. Then this will imply that dimension of So here you put 0, yeah, so this will imply that dimension of x is equal to dimension of f of x. So the dimensions are and equal to dimension of y. Yeah? So f of x will be dense in y. Okay.
And y can be an arbitrary point with this property.
What?
Y. Take y.
Because y can be arbitrary because you just substitute it in this equality. So 0 will be bigger or equal than this one, so you see that this should be 0, yeah, because it is positive. And yeah, so I realized that I have done a misprint here. So here not h has finite number of fixed point, but an element. So some element of h. Of h has a finite number of fixed points of G mod h. So now the question is the following. So you're picking up G. So here you have, so naturally in the set that of all conjugate elements, so why the condition really asks something about H here, so an element H. Because this is element that you definitely know will be inside the image, so inside this set, yeah? Inside the image of our map. So take, here you take the element H. And you are asking about the following, so you are asking about, so you have W here in G times H times x, yeah? And it maps to G equal to x via the second projection, yeah? So you have a fixed element H here. So we ask what is, so we are considering the map from W. So W has dimension. So dimension of W is equal to dimension of X, which is G. So you want to consider the second projection to X. And so this means that you want to have the fiber of the restriction of this projection of so Px inverse of H. Yeah? Okay. So then you are raising the following problem. So H is already here inside X, so you put H to be here in the second factor, and ask which element G can be put here. Yeah. So so this means that, so here you have the corresponding coset. Yeah, so which element G can be put here in order that, so which G can be put here in the first, in the class GH, so such that, so what is the condition? So notice that if you look at what is what is the relation with W, you should be able to via this element to out of H to make the just after application the inverse of G. Yeah? So you should be able to obtain still the elements of H. Yeah? So just this means that H can be obtained from some H tilde via conjugated it by G. Yeah? So this is fixed H, and this is just element of H. Yeah, so in order to match that the element is in W, so you are picking here the element of H, you are moving it by the element of G. But if you start with, if you want to say what elements are over the phi by H, these are those elements G such that G times H, the application of G to H, is equal to H. But our action is conjugation. Yeah? So here you should solve this problem. But this problem is equivalent to the following, that you take H G, yeah, so, and it is equal to G H tilde. And this is equivalent to saying that H, the coset of GH sits in GH. So H fixes GH, the coset inside G mod H. So which is precisely the condition of the theorem. Yeah. So this set is finite. So this set is finite by our conditions. Okay. Yeah, so notice that here, this map is conjugation here. Yeah, so that's why I'm writing down this equality. Yeah? So this is saying that there exists H such that GH. So a general statement in terms of Z, so this means that there exists, we fix Z, yeah? And we are finding G and Z tilde such that, so Z tilde in Z such that G of Z tilde is equal to Z. Yeah? And our action, so if you substitute H and Z, so here our Z plays role of H, and action is conjugation. So, and Z tilde plays role of the Z tilde. So that's why I'm writing down this equality. But this is equivalent to the following statement. So the existence of this equality for arbitrary, so H is fixed here. So H is not fixed. It is an element of H. So finding this pair G and H is equivalent to finding a coset. Yeah, so this, writing down the coset, you may forget of telling that H is inside H. And then this is equivalent to that coset is a fixed point of H. Okay? And the choices of such cosets is finite, so this means that this set is finite. Понятно или что-нибудь пояснить? Уже время позднее, ладно.
Можно по линии вопрос?
Да.
Если слой пустой, у него как-то определена размерность?
Ну, как бы...
То есть все слои пустые, это все очень странно.
ну, в каком смысле все слои пустые, да? Ну, в частности, как бы в частности, эта лемма говорит сюррективность, да?
Ну, то есть это мы смотрим слои над всеми точками, а не только над теми.
Ну да, ну то есть как бы в частности условие леммы, да, говорит о том, что слой над всеми точками, да, он не пуст. Потому что я говорю о размерности его.
Ну, то есть
Ну, -1 говорят размерность. Размер, да.
можно было бы так взять прямую без точки и вложить в прямую?
Ну правильно, но это запрещается тем, что размерность всех слоев должна быть одинаковая. Размерность пустого множества -1. Поэтому она не 0.
Вот у нас есть теорема
Да.
по непрерывности.
Да.
Мы бы могли сказать, что тогда образ — это множество таких точек, где размерность хотя бы 0.
Да.
И оно получается замкнуто.
Да.
Получается, что нельзя говорить.
Получается, нельзя говорить, что размерность пустого — это пустого слоя — это -1.
Потому что там есть размерность больше, равна n.
Ну она сейчас, ну...
Сейчас это прообразно, что там.
Нет, вот как раз именно поэтому мы не говорим об образе. В теореме о размерности слоев мы никогда не говорим об образе, а про образе. Да, там все верно. XK это, ну я всегда пишу f от x а потом применяю f-1. Это специально сделано, чтобы у вас слои были не пустые. Но это как раз вот эта причина, почему функция ведет себя полунепрерывно сверху, но снизу уже так не получается. Поэтому вы правильно мне это сказали, но не поймали.
Кстати, когда мы применяем сначала f на -1, да?
Да.
Мы всегда получим многообразие или не обязательно?
Мы по конструктивному множеству получим.
Там можно, скажем, вот в f-1 есть какие-то...
Нет, ну это то же самое, что и просто прообраз чего-нибудь.
Ну, не совсем. У нас же образ, например, мы знаем, что он там конструктивный, прообраз конструктивный.
Да.
Потому что ты можешь самому этому множеству, если есть конструктивное множество в x, то вот ты в него фигачишь f, потом f-1.
У нас совсем не нравится. Не факт, что...
Ну ладно. Угу. Ну хорошо.